Let's learn about limits. Limits are great because even if we have like a really weird function that we have no idea how it behaves, they'll let us think about how it behaves at a particular point, which can be very useful for a lot of different applications and is the foundation of basically everything in calculus. Limits are kind of just like finding a pattern or finishing a sequence. Here we know that the next number is going to be 6, but we can also figure out a sequence in the other direction. So we know that we're counting up by 2's here, so this number is going to be 12. And likewise, we can just figure out a number in the middle of a sequence. We know we're counting up by 3's, and the last two numbers, 15 and 18, also confirm that. So we know this number is going to be 12. But at the same time, we can have a sequence where from the left side it looks like one thing. We might think that the missing piece might be 4, but if we look at it from the right side where we're counting up by 2's, we might think that the missing number is 8. And in situations like this, we can kind of just say that there isn't an answer that's going to work for both sides. So a solution does not exist. And we can do the same thing with functions. If we just have a straight line going upward and we ask, what is this function going to be at 0? Well, we see it's headed straight towards 0. So the limit as it approaches 0 is just going to be 0. And if we have this random curve that approaches the y-axis like that, well, we see that no matter what all this stuff going on over here is, as it gets close to the y-axis, it's approaching the y equals 3 points. The limit of this function, as x gets close to 0, is going to be 3. But now what if we have a weird function like this and we want to find the limits at this value of x? Well, if we look at it from the right side, we see that it's just constantly y equals 1. So we'd say that the limit is equal to 1. But if we look at it coming from the left side, well, it's just constantly -2. So we would guess that the limit is just going to be -2. But in this case, the numbers don't agree. So once again, we would just say that the limit does not exist in this case. Now here we have a function that actually isn't defined at x equals 0. You can see if we just plug in 0 into the denominator, we get 1 over 0, which is undefined. But we notice that if we look at it from the right side, it's blowing up to infinity as we get closer and closer to x equals 0. And from the left side, it's doing the exact same thing. It's blowing up to infinity. So we could say that the limit as x gets closer to 0 is actually infinity. Even though the function itself can't be defined at x equals 0, because we're approaching infinity as we get closer to x equals 0, the limit is still going to exist and it's going to be infinity. But if we remove the absolute value of this function, we still get the right side blowing up to infinity, but the left side is actually going downwards because we have 1 over a negative number. And so this is actually going to go to what we call negative infinity. And because this negative infinity is not the same as the positive infinity that the right-hand side goes to, we can say that the left and the right sides don't agree. And so the limit as x approaches 0 is actually not going to exist here. So as general notation for these limits, we have the abbreviated LIM. And beneath that, we have x with an arrow pointing to some number. This is going to tell us what x is approaching as we're evaluating this limit. And then we have the actual function that we're taking the limit of. Here are some limits for you to try out.